Hi, good afternoon, good morning, everyone. Um, so I wanted to do a quick stream to basically finish off what I didn't get a chance to do yesterday. Um, and that is trying to run Micropython off the HyperRAM that we added yesterday to the SoC on the iCEbreaker. So I'm not. This should be I'm hoping a relatively short stream, um, because I'm not starting off from nothing. I actually did like a year ago or something. I actually ported Micropython and got it to run on the iCEbreaker, but just off the single port RAM, which means I only had 128K of RAM, and that had to include the entire executable code, which for MicroPython, even compiled for the minimum configuration, is like 112K or 120K, which means there was very little RAM actually left to do anything, um, and no room to add modules and stuff like that. So it was just really a proof of concept. So just this afternoon, I updated the code that I wrote a year ago to the latest version of MicroPython and pushed it on GitHub. So it's not on GitHub on the MicroPython repository, and we can actually, yeah, I have it running here basically. So if I go off here, so that's the code. It's relatively straightforward. I basically just copied. There's an example like a minimal port, and I just copied the file and adapted like the minimum amount, which pretty much it was only changing the method to drive the UART so that the console can actually talk to the host, and changed some configuration options. So there's an include file where you can define a bunch of stuff, and mostly I just changed the name and removed stuff that was ARM Cortex specific, and the other thing is the startup code. So you need to initialize the hardware and stuff like that. So I just included my kind of standard C initialization code that we used yesterday as well, included it here. And finally, it's a link script that basically tells, okay, where do the various section need to be linked at and placed in the firmware and stuff like that. And you can see like in the memory currently the only zone that's defined is a single port RAM zone, which is mapped to this address and is 128 kilobytes. Okay, and so if I go and build this, let me okay, wait, it's already built, of course, but let me just do make clean, then rebuild it. So it's linking everything. So you can see that the final binary here is like 126 kilobytes. So that pretty much uses the entire memory. But if we connect to the yeah, that's the console launched on the iCEbreaker, and you can see the 123 thing is like the boot up debug, and then you've got the MicroPython running, and you have your MicroPython running on the iCEbreaker. So that's kind of the starting point that I was working off, and you can check that you have very little memory available. Like I only have like 12 kilobytes of memory, basically free for the user to use in MicroPython. And so what I want to do now is basically take that code and adapt it, and instead of running off the SPRAM is to run it off the HyperRAM, basically, which should be straightforward enough, right? So the first thing I need to do is actually rebuild or rather reinstall the code that we built yesterday, because currently on the iCEbreaker I have another design loaded. I have the sock without the HyperRAM and without the cache, and with just 128K of SPRAM allocated to the sock directly, so I could run my old version of Micropython. So now I'm just gonna rebuild and reload the stuff that we finished yesterday. And then I need to flash the firmware as well. Yeah, I didn't make clean, so I need to actually rebuild the entire Bitstream, but that should be fairly quick. Come on. Routing always takes time. So yeah, I want to get that up and running, and then I want to compare it to other Micropython. I don't actually have any other board that actually runs Micropython, but I have a Formu that runs CircuitPython, and I have the Serpente board by Arturo, which runs CircuitPython as well. And I want to run like a couple of test scripts, just really dumb stuff, just to get an idea of how slow it's gonna be compared to other implementation. Like I fully expect it to be slower than the Serpente by a lot, probably, just because that's like I don't know, it's like an ARM running at 48 megahertz, which can execute like one instruction per cycle, and I have like a sock that has a 24 megahertz CPU that takes like 4 cycles to execute each instruction. So it's definitely gonna be slower. I just want to see exactly by how much, and I want to compare it to the Formu, which runs on a VEX RISC-V, not a PyCore-V, at 12 megahertz, and it runs off the flash memory. And it has a cache memory integrated to the VEX, but I don't know how good it is and how well it performs or not. Okay, so it built the firmware. Let's see if we... Okay, so our firmware is running. The HyperRAM seems to be working. And we have... Yeah, the... running off the mem test that we wrote yesterday, just to see that, okay, everything is running as expected or something. Okay, it takes a bit of time to run. Hey Matthew, welcome to the stream. Yeah, I mean you didn't miss much. I basically just oh yeah, I mean I'm planning it for it to be quite short, but yeah, I know it's not an ideal time, but I'm busy later, and I also want to follow. Peter is streaming tonight about Lytix setup on the iCEbreaker. I definitely want to follow that. and I wanted to finish this stuff today, so that's why I'm doing it right now. There will be the recording and stuff like that, so if you can't stay, you can check out that. Okay, so I've restored we have our sock loaded in the iCEbreaker. It has the HyperRAM running. That's basically the state we were at yesterday. So what I'm going to do now is take the... So that's the Micropython code that I wrote like a year ago for the iCEbreaker, and what I want to do is run it off the HyperRAM. So the first thing I'm going to do is change the link script, because we're not loading code in the SPRAM anymore, so we need to link at a completely different address. And so this is going to be linked here. That's where our HyperRAM is mapped, and it's also much larger. So we have 32 megabyte and not 64 megabyte of HyperRAM. So let's see. Okay, so now we're linking at the right place. We need to put all the section in there. HRAM. So what I'm planning to do is basically load it entirely into the HyperRAM, and like the test firmware that I currently have in the single port RAM will load Micropython from the flash, copy it to the HyperRAM, and jump to it. That's basically the general idea. Okay, so it's relinked. So if we rebuild it, it should be linked to the right address. We need... Okay, I need to check the startup code to see if there's anything that's specific to the... address it was previously loaded. No, it takes all of its address from... All of the address are taken from the linker symbol, so that doesn't need changing. So that looks fine. What I'm gonna do is change this as well. 9.c. Yeah. So currently the heap of I call it like in quotes because it's not really a heap, but the code where Micropython puts like its own managed memory. It's just a static array of 12K. That's what was previously allocated. What I'm gonna do is manually specify it to be in memory. And I'm gonna place it at this plus 1 megabyte. Yes. And I'm gonna allocate like an entire megabyte of no, I think it's begin and end, usually the symbols, rather than start and stop. Like an entire megabyte of memory for the Python object, which should be way enough for Micropython to do its thing. So here you see we call GC init, which basically tells Micropython where is the memory it can use. And currently it was like a static array, and now I'm just gonna give it like addresses in the HyperRAM directly. There we go. Oh, also because we don't directly boot to we won't be directly booting to Micropython. We will still boot to our old firmware and then have it load Micropython from the flash. I'm gonna flash Micropython to another offset, like 1 megabyte inside the flash, just basically out of the way. So, okay, this should build, hopefully. And it's flashed. Okay, so now we have our Micropython binary loaded in the flash, and it should be ready to run off the HyperRAM. The only thing that we need to do is take it from flash, copy it to the actual HyperRAM, and then jump to it. So let's do that. Where do we have this? I can't remember the name of the file. Film. Okay, firmware app.c. So I already have like a method to what the fuck did I do? To read from flash, because this firmware actually implements DFU already, so it has all the flash access function already written. So I can just call that. However, all of these access are made like in single burst, which means I can't read more than a page at once. So I'm just gonna do it like chunk by chunk of 256 bytes at a time, and I'm gonna copy, let's say, 256 kilobytes of data. So the HyperRAM is mapped to 1, 2, 3, 4 this address, and the flash. So we flashed the binary at offset 1 megabyte, which means that we can start at this address. So we want to copy 256 kilobytes, and we do it one page at a time. So this method, the flash read, is really not a very fast method because it's not been optimized. It doesn't use. It uses the like a built-in controller, SPI controller from the iCE40, which is pretty slow, but it doesn't matter much for now because this is gonna get replaced at some point anyway. Okay, so this should this should load the Micropython binary inside the HyperRAM, and now we need to jump to it. And so defining a function pointer and then calling this. I think that should work. Let's do that. So we still need to initialize the HyperRAM, and then there we go. So that's Micropython running of the HyperRAM. It was really just a matter of changing the address to get it to run. And I mean, that's the whole point of doing the cache and just memory mapping it, is that it just appears as normal memory and we can just load code to it and jump to it, and it works. Cool. So now what I want to do is run a couple of just quick tests. I wrote like a simple LFSR implementation in Python. Let's just me copy that to the streaming machine. Let me Okay, so that's just a simple LFSR. It's not even like optimized or anything. The point is not to go fast. The point is just to compare different implementations. So I'm gonna take the same code and run it on this implementation, run it on Serpente, and run it on the CircuitPython running on the FOMU, and just see what kind of order of magnitude speed we get on the various platform. So I'm just gonna copy the code. Okay. Okay, so I'm gonna time this with my phone because I don't have an implementation of a timer in MicroPython. Like the port is really basic, so I don't have an implementation for time or anything like that. So I can't use it to benchmark itself. I'm just gonna run that statement, which basically generates 256 random numbers for using that LFSR running 16 steps, and then it sums all of them, which is it's not meant like as a like a universal MicroPython benchmark. I just wrote some Python code that I thought would run and only use like integer operation, kind of basic stuff, but still call objects and stuff like that to have kind of an idea of what speed it executes at. So I'm gonna try to not mess up and press the enter at the same time and I press start on my phone. There we go. Okay, so that took 11.61 seconds. Yeah, that's the time it took to run it. I'm gonna do it a second time just to better idea to make sure that it's actually run correctly. I'm gonna actually reinitialize the LFSR object. And run it again. Okay, reset and go. Yeah. So now I have 11.60 seconds. So that's pretty consistent. Okay, so that's one data point. Now let's try on this. So that's a Serpente by Arturo, which runs CircuitPython. So CircuitPython is not exactly the same thing as Micropython, but the actual Python part and the compiler inside and the JIT and stuff is, as far as I know, the same. So the result, I think, should be comparable. If anybody knows better, please correct me, but I think that's the case. So I need a USB-C cable. Let me wire that up. Okay, so it's connected, and we can say predict Serpente Arturo with a very long serial number, and ACM is registered, so it should be on ACM1. So I should be able to just quit this, launch it on ACM0. Yeah, of course I need the permissions. Okay, so I've got CircuitPython running. I'm not sure if it's the latest version or not. I didn't update it since I got it in at last Congress, but I'm assuming it's fairly recent. Like, yeah, it's like less than 3 months old, so there shouldn't be a huge performance difference, right? So let's load the same code. Same code is loaded. Initialize the LFSR object. Prepare to run this. Yes, Serpente. So let's do 2 runs as well. Okay, so that was much quicker. That's the timing number. So it took 2 seconds, 2.49 seconds to run that benchmark. Which, as expected, is noticeably faster, right? I'm gonna run it a second time just to make sure. There. and I was a little bit less consistent. I have 256. So again on this run. So yeah, I mean, of course, as I said, it's CircuitPython, so it does have some things to run in the background because it includes like the USB stack. However, there is no USB activity whatsoever. Like during the benchmark is running, I'm not accessing the disk, so there is no USB packet being exchanged or anything, which means that pretty much all the CPU power goes to running the actual Python. There is no I/O or anything like that. So it should be fairly comparable to the Micropython performance, I think. But it's, I mean, let's check the, I haven't actually checked the CPU. I think it's a 48 megahertz Cortex M0 Plus. Is that? That's what I have in mind. Yeah, it's a Cortex M0 Plus. So the plus means that every instruction executes in one cycle, and it runs at 48 megahertz, right? Yeah, 48 megahertz. I mean, it says maximum. I'm assuming that he's running it at the maximum frequency. I didn't actually check, but okay, that might not. Is there a specification somewhere? Yeah, it's running at. Yeah, I mean, I see no reason why it wouldn't, right? But so yeah, it's running 48 megahertz, and one instruction per cycle. So obviously, it's gonna be faster than a CPU that's running at 24 and takes 4 cycles to execute in each instruction. Oh, it has an internal clock. So yeah, there is no. I didn't even look at the board, but yeah, there is no crystal oscillator, right? So yeah, okay, thank you. And oh, hi, Timon. So now let's try the other platform I wanted to check, and that's the FOMU. I need to find it, which is kind of always an issue with something that small. What do I do with it? Okay, yeah. Here it is. I mean, you can barely see it. That's a FOMU, right? It's the hacker version, but that shouldn't change anything performance-wise. Let me disconnect this and connect this instead. Okay, so I did just update the bootloader on that FOMU to make sure I could actually run. I actually need to download CircuitPython for that. Releases. So that's the latest release. CircuitPython. That's save file. Not sure if it's done downloading. Yeah. So I need to flash it. Damn it. So it's disconnected and it re-enumerates itself as a formula, including the CDC ACM. So I should be able to just do the same. No. ACM 0. Oh wait, is that? Wait, what is that terminal? Okay, never mind. There we go. So I have CircuitPython running on the formula here, and so I should be able to do the same thing. Oh, wow. Yeah. I mean, I tested this before. I knew it was massively slower. I tested it with another benchmark, not this one. But what I'm going to do here is run it with... instead of doing 256 cycle, I'm only going to do 16. Because that's what I had to do with a different benchmark for it to actually finish in a reasonable time. And let's time this. Ready, go. Okay, so this took 16 seconds to run only 16 iterations instead of 256. I'm gonna do a second 16.44. I'm gonna run it again. And you can see that even the console is massively slower, but the console, you know, that could be the USB because the formula, in CircuitPython, you have to run the USB stack, but the actual computation shouldn't use anything USB or anything like that, which means that it should be a fair comparison. Reset. Let's run that again. This time I got 1629. Of course, those numbers are for only 16 at iteration, which means I should multiply them by 16 to get the time it would take to run. So there we go. So if we take the Serpentine as a reference and we do So that's like 4.5 times slower. That's 1 time slower. And if we compare this, it's like 22 times slower. Okay, so we could, I think that's pretty much what I expected. Something I might actually, yeah, I'm gonna actually do that, is I'm gonna run, instead of running it off HyperRAM, I'm gonna run it off the internal SPRAM entirely. So that's basically what I had running at the beginning of the stream. Just to see the difference between running code off the HyperRAM and code running off the internal SPRAM. Because we have one additional, clock cycle to fetch from the cache. So I would expect this to be slightly faster than from the HyperRAM, but not too much, hopefully, because the cache should be doing its job and we shouldn't be hitting the HyperRAM too often. So let me set up for that. So what I need to do is to build a Bitstream here. Okay. So I've just switched to a tree that doesn't have the HyperRAM controller, and what I'm gonna do is bump the memory to 128K, so I can actually run something else is we can actually see here that we should have 1 megabyte of, we have 1 megabyte of memory available here now for all the Python objects, which is probably way more than we would ever need. But in case you have large Python object, you can do that. And I mean, I allocated 1 megabyte, but we could allocate like 31 megabyte if we want to. So let's see. Yeah. Okay, so I have my Bitstream loaded without SPRAM, and now I need to load the old version of the code. So all the changes that I did here to adapt it to the HyperRAM, I'm just gonna stash all of that. Except for that one, because that's the compiler. Flash that directly. So hopefully we should see this rebooting and boot into Micropython. Okay, so now we have the Micropython running directly off the SPRAM. We can actually check that, because if we check the amount of memory that we have, Yeah, now it's 12K instead of 1 megabyte. So let's run our benchmark. Oh, you know what? I pressed the wrong key. I have no idea how to get out of that mode. Just gonna redo this. Okay. Yes. There we go. Initialize FSR. And run it. So what kind of number would we expect? Because previously every instruction fetch, every executing each instruction would take, I think, 3 or 4 cycles. And now with the HyperRAM it would take 4 or 5. Something like that. I don't remember. So it would be between between 25 and 30%. No, between 20 and 25% slower, just due to the additional cycle to access the cache. That's what we would expect. And then also there's the fact that every time there is a cache miss, we need to go fetch code of the HyperRAM. But hopefully here our active set should fit inside the cache, and so we should really only pay that price once. So let me time this, reset, go, 3, 2, 1. Nine seconds and 63. So 963. Let's do that again just to be sure. Reset. 3, 2, 1. Yeah, 968, so pretty consistent. So if we do this, so this would be this divided by this. So yeah, we can see that when we're running off the HyperRAM, we're basically 1.2 times slower than we could be if we were running entirely out of the SPRAM. Now, most likely, as I said, most of that is probably gonna be due to the fact that we've added 1 cycle of latency when fetching instructions, and that's because we use the wishbone bus. And in a previous stream, I think it's in the stream number 4, I think. So not the last one, the one before that. When I explained the bus adapters, I was saying we could actually, instead of using wishbone, we could connect directly to the PyCore-RV bus, and it has a look-ahead interface that would allow us to pre-fetch all the tag information for the cache and basically not have to pay that price. And at that point, we would basically have HyperRAM code running at the same speed as the SPRAM, maybe maybe like 1% slower because when there is a cache miss or something, but that would allow us to gain most of that back basically. That seems something that I need to do, but that's probably that's definitely worth doing, I think, because it's slow. It's slow enough as it is. Yeah. So. So Timon, no, I think here the bottleneck is not the RAM. I mean the reason why the iCEbreaker is slower than the Serpente is just the clock speed and the softcore implementation, because the Cortex M0 Plus running at 48 megahertz can pretty much execute 48 million instructions per second. I mean, like it's simplified. Some instructions are slower, of course, but most of the operation register, like addition, moves, and that kind of stuff, only take one instruction, right? On the Pico RV, each instruction is not executed in one cycle. It's executed in here in this case, it would be like 4 cycles, I think, to execute each instruction, which means that it's running at 24 megahertz, so it's already slower, and it's divided by 4, so it would only execute about 6 million instructions per second. And so if we do 48 million instruction for the Cortex M0 divided by 6 for the Pico RV, we would have a factor of 8. So so it's actually not that. It's actually performing better than I would expect. Yeah, the iCE40 is really not a very fast FPGA, right? So the Pico RV is only executing here at 24 megahertz. So that's explained part of the latency. So honestly, I'm actually somewhat happily surprised, because if we run it off an ECP5, for instance, that could run the Pico RV probably at maybe 72 megahertz or 96 megahertz, it would be basically 3 times faster, which means we would actually get to the same kind of speed as the Serpente. I mean, or any native board. I just use it because that's the only native board I have, right? And then we could also use the VEX CPU, which has a better clock per instruction. So instead of taking 3 or 4 cycles to execute each instruction, the VEX RISC-V softcore only takes 2 or 3. I think, less than the Pico RV. So that's something I still need to test. As well as to use the VEX instead of the Pico RV. Unfortunately, because it's not a drop-in replacement, they have different interfaces and stuff like that, so I can't just flip a bit and replace it. That's where things like Lytix would shine, is to easily switch between implementation and stuff like that. But here I'm using Verilog, so it's not as easy. And now the reason why the FOMU is so much slower, because the FOMU is running a VEX CPU at 12 megahertz, so it's at half the clock frequency, which is already not good for performance, but it's much slower because the code is running from Flash, and although the VEX has an internal cache, well, it seems obvious that despite that, the VEX internal cache is really not that good, not that efficient, because I mean, look at the numbers, it's quite a bit slower. Yeah, but that's actually part of the stuff I'll be working on, but not on stream. I don't know when I'm gonna do that. But it's basically work on instead of using HyperRAM, I said it's using SPI PSRAM. So the pseudo-static RAM that you find that's actually used, like for instance, on the Tiny Pico. Yeah, the Tiny Pico uses. Oh, actually, I should have benchmarked the Tiny Pico. I have one. That runs Micropython, right? Let me see if I can find my Tiny Pico quickly, and maybe we can run that on the Espressif to see what kind of speed it achieves. Yeah. It's CircuitPython versus MicroPython, but from looking at it, like the Python runtime, like the actual Python runtime part, seems to be, very similar. So I think the performance should be easy. Somewhat comparable. At least have some validity in comparing them, I think. But maybe I'm completely wrong. That's why in the benchmark I run, I use like very basic features of Python, so that hopefully they're not things that have been optimized for in either of them. So that's a Tiny Pico that's made by the Unexpected Maker. Sion, I think. I don't know how to pronounce his name properly. Let me connect that up. Of course, that's a micro USB. Damn it. So I need to disconnect the iCEbreaker. I'm not sure I ever used the Tiny Pico yet. I bought 2 of them because I figured that's useful to have in. Okay, so it appears as a USB port, as a USB thing. So it's TTY USB 0. Okay. Yeah, of course. So oh, I don't get a shell like a RPL. I don't know how to interrupt. Has anybody used a Tiny Pico before? Maybe I should have looked that up. So I completely forgot that I had it. Well, it's already loaded. Yeah, I should get a RAPL, right? Which I don't. I get temperature readout. Maybe I flashed something on that board? Let me try another one. I have two of them. Well, it's doing the same thing, so yeah, unfortunately, I've never used them, which means I have no idea if I'm supposed to get like a Python shell when I start them or not. I guess not. That's for the ESP32. Yeah, I mean, I would have expected a shell as well because that's like Micropython is what I executed on the iCEbreaker. It's not CircuitPython. It was Micropython, and I get a RAPL directly. Yeah. Yeah, okay, that's, thank you. It ships with Micropython installed. Well, okay. Yeah, but how do I stop it? Okay, that's not working. Shit. Damn it. Yeah, thank you, Mike. I'm having trouble copying cut and pasting between between the chat and the console that broadcasted because it's running inside a nested X server, so I can't cut and paste between both. But I think that's the I'm supposed to talk about taking a few. Okay. I mean, I can try, I guess. So I need to shut down, I guess, this. Okay. Yeah, I hope so. But no, I need to actually refresh Micropython, right? Tiny picker. So I guess that looks good. Yeah, I think it's just easier to try just format everything and reload from scratch, and we'll see if that works. Hopefully it does. Okay. I have nothing now. Is it another baud rate? Maybe 1 megabit? Yeah, true, I can try to reset the board. I need to disconnect it. I don't know why it doesn't quit, that's just annoying. Okay, disconnect completely. Nope, that's not doing anything. The LED is flashing. I'm not sure I can frame that. I don't know if my USB cable is a little too short, but you can see one of the LED is flashing. But other than that, it's not doing anything. Wait, it's actually... Okay, so it was using baud rate. So I can try that baud rate, maybe that's... Oh, wait a minute, maybe I have to... No, that doesn't change anything. Shit. What are the other parameters? I disabled hardware flow control. Yeah, there we go. Okay, the CP select the uses the hardware flow control, and so now I have access to Python. How much memory do I have actually? Oh wow, nice. Okay, so let's run our benchmark. I mean, if you can call that a benchmark, but I'm somewhat expecting that it's gonna completely explode the time of the the icebreaker. Okay, restarting my stopwatch. 3, 2, 1. Okay, yeah, I don't even have the time to press start and stop. Yeah, it's like that's about what I'm measuring. I'm gonna increase it and run that 16 more times, just so I get a little more valid number. Okay, so it took 6.10 seconds. But that was to run 16 times more iterations, so that's like 0.39 second or something, which yeah, it's like 6.4 times faster. So the tiny Pico is significantly faster. Oh yeah, it's like six times faster than the Serpente. The SP runs at 240 megahertz. That's what. Can I actually find the spec for this? Yeah, 240 megahertz. It's dual core, but I'm assuming Micropython doesn't actually use that. So 240 megahertz, so which compared to 48, it's five times faster. So and we benchmark it at about 6 times faster. So yeah, it's pretty much all the gain is probably the clock frequency. And the rest is, yeah. So I think I'm gonna stop here. I kind of did what I wanted to know, in the sense that I can run it on off the HyperRAM, so running code of there works fine, and I can probably gain the performance to get very close to the SPRAM performance. Of course, currently the Micropython port is really basic. There is no module or stuff like that. We need to add module to support for the peripheral and stuff like that. That's something I can do later. I just wanted to basically have an idea if it's even worth to do, or if it's gonna be too slow to do anything useful. And I think it's definitely not the fastest, but it's definitely fast enough to actually be useful to do some light stuff. Especially if you use it for like the high-level control logic and driving accelerators implemented in hardware, things like that. Okay, I think as I said, I think I'm gonna stop here. Thank you everyone for joining. If you haven't seen the previous streams, you can see them on Twitch or on YouTube. They are all there. Well, actually, need to refresh that. This one will also be uploaded. And if you have any question, you can find me on IRC or on Twitter under @TNT or on the Discord chat of the 1-bit square Discord chat. Okay. Thank you again, and yeah, see you next time. I don't know when that will be or what it will be about, but bye.